Okay, so we're going to recap this from 2.8 yesterday, and then we're going to do 2.9, hopefully all of it, not all of it, most of it, this period, and that'll wrap up our chapter for us. All right. First problem, F plus G. F has a denominator, G does not. What do you need to be able to add them together? Common denominator. So how we do that is I'm going to take function G, 12 minus 8x, and to get a common denominator, we're going to multiply by the denominator we want, x plus 2, on the top and on the bottom. So that means we're really just multiplying by 1, something over itself. It's going to change the way it looks, but not really what it's equal to. So my first fraction stays the same. My second fraction will now have a denominator of x plus 2. And in the numerator, you're going to need to FOIL those together. You should have, from your first terms, a 12x, your outside terms, a 24, your inside terms, negative 8x squared, and then your last terms, negative 16x. Final answer, when I add them together, there's still going to be that x plus 2 in the denominator, and then we're just going to add all of our like terms on top, which will be a negative 8x squared, a negative 4x, and then a positive 25. Okay. This is also one we had to find domain of. What can x not equal here? X cannot equal negative 2. That would give me a 0 in the denominator of the original function f or in the answer that we have here. So your domain should be everything except negative 2 in interval notation. Negative infinity to negative 2 and negative 2 to infinity is what you should have on that one. Okay. Questions on A? B, we are multiplying them together. So I have 1 over x plus 2 times 12 minus 8x. You can think of that as over 1 if you want. We're multiplying straight across. 12 minus 8x over x plus 2. And then you want to look to see if you can reduce this at all. You could factor a 4 out of the numerator. If I factor a 4 out of the numerator, I'm left with 3 minus 2x, which does not give me any common factor, so it does not reduce. So this would be your final answer. And domain, again, is everything except negative 2. So negative infinity to negative 2. Negative 2 to infinity. Part C, we are dividing. Remember dividing, instead of G divided by F. Why are my colors not flipping there? Let's try that again. There we go. Instead of G divided by F, we can do G times the reciprocal of F, which is going to be a little bit easier. Function G, 12 minus 8x. Function F, if I take its reciprocal, if I flip it, is just x plus 2 over 1, or just x plus 2. So we're just foiling. Now we actually foiled that, those two pieces together up in part A, so you can use part A to help you here. You're going to end up with a negative 8x squared, a negative 4x, and a positive 24. Domain, again, of this one is everything except for negative 2. Even though negative 2 is not a restriction in the final answer, we used F to get it. So that carries through the problem. D and E should have been a little quicker. Function D, or letter D, we start with f of negative 2. We work from the inside out. F of negative 2 means plug negative 2 into function f, which actually ends up being undefined, which means this whole problem will be undefined. Can't go any further than that. Letter E, again, starting in the middle, I have g of 4 If you plug 4 into g, you'll have 12 minus 8 times 4, so 12 minus 32, which is negative 20. Now I find f of negative 20. If you put negative 20 into that denominator, you're going to have negative 1 over 18, or 1 over negative 18 would be the final answer on that one. Okay, last but not least, letter F. What am I plugging into what there? F of g of x. What's being plugged into what? G is being plugged into F. Okay, so that will look like 1 over 12 minus 8x plus 2. And you can put the 12 minus 8x in parentheses if you want, but you don't need them here because there's nothing to distribute. Final answer is going to be 1 over 14 minus 8x. As far as the domain is concerned, x cannot equal negative 2. That comes from the original function f. And we also have an additional domain restriction here. You can take your 14 minus 8x, say it cannot equal 0, and then from there solve for x. You'll have to subtract 14 and divide by negative 8, which will give me positive 14 over 8, which reduces to positive 7/4. So your domain is everything except those two numbers, which will be negative infinity to negative 2, negative 2 to 7/4, and then 7/4 to infinity. When we have two domain restrictions, it's splitting that number line up into 3 different segments that we're getting there. Okay, so a little review of our composition, combining, everything's kind of put together here, all of our domains. Any questions on any of those ones? Nada? No? Okay. The ones on the bottom should have been a little bit faster. F plus g of negative 3. Get a pen that works. There we go. That's the same as f of negative 3 plus g of negative 3. F of negative 3, go to negative 3, go up to function f, you get positive 1. G of negative 3, again, go to negative 3 on the left, and you have to go down to function g, which is negative 1. Final answer on that one should be 0. Second one, you're doing f of 2 times g of 2. F of 2, you're just going to go 2 to the right, go up to function f, that takes you to 4. G of 2, 2 to the right, go down to function g, it's a negative 6. Multiply them together, negative 24. Third one is composition, work from the inside out. G of negative 3, so I'm going to go negative 3, 3 to the left, go down to function g, that's negative 1. So the inside becomes negative 1. Plug negative 1 in, so negative 1, 1 to the left, up to function f. Final answer there is positive 1. Okay, last but not least, composition, decomposition. I will give you a couple different ways you can do these. These are probably the most common ways that you're going to see them written, but lots of different answers for these. Notice the way that the notation is written here. G is being plugged into f. So if I'm going to do these problems, I'm going to start with function f, and then I'm going to fill out what g has to be plugged in to get me that final answer h. So for this first one, I'll say f of x equals the square root of x plus 3. Okay, so my basic parent function plus 3. And if I make my g x minus 5, that will replace the x under the square root and give me the function I'm looking for. Make sure when you write these, there's a variable in every function. The second one, I would do f of x equal to 7 over x, and I would do g of x equal to x plus 5. Again, the x plus 5 would replace that denominator and give me the function I'm looking for. Last one, I'd probably do an absolute value for f. And I'd make g everything that you see inside that absolute value, 5x minus 1. Again, those aren't the only correct answers, but those are, again, probably the most common ones that you're going to see for these. Okay. All right. So that's our little recap of that big lesson 2.8 that had all of those wonderful things in it. What questions do you have on it before we move on? Nothing? How's homework going? Good? Has multiple parts in some of the questions. I know, that's not fun. Other than that, no major issues? Okay. Remember, homework is due next Wednesday, so a week from today. 2.8 and 2.9 are going to be due. All right, I have a 2.9 worksheet for you, the big ideas. So give me a second. All right. All right, inverse functions. So in order to talk about an inverse function, you first need to know if a function is one-to-one. So this kind of is similar to when we talked about just the definition of a function at the very beginning of the chapter. At the beginning of the chapter, we said something is a function if each x has exactly one y. And there were a few different ways we saw that with like the graph. We did the vertical line test and we saw the correspondence diagrams. We saw different sets of points. There were lots of different ways to determine that. But a function is when each x has one y. A one-to-one function is a special case of a function. If each x has one y and each y has one x, so it goes both directions, then we have a one-to-one function. Now, why is that important? Because if a function is one-to-one, it has an inverse. It is invertible, and that's what we want to be able to do in this section is find an inverse. So you have to know first, is it a one-to-one function? Could it be invertible? So I've got 3 correspondence diagrams here. These are pretty quick. I want to ask 2 questions for each of them. First question, is it a function? Does each x have one y? Second question, does each y have one x? So in this first correspondence diagram, does each x have one y? It does not. Where's the problem? X base 2 there, yeah. Oop, Pango, come on. So because each x does not have one y, it's not even a function. If I graph this, it would not pass the vertical line test, so it definitely is not going to be one-to-one. Looking at the one in the middle, does each x have one y? Yes, each x goes one y. Now look the other way. Does each y have one x? No. Where's the problem? y2. Okay, so it's a function, but it is not one-to-one. Okay, and then what about the last one? Does each x have one y? Does each y have one x? Yes. So this is what a one-to-one function will look like. Okay? Make sense? Just a function backwards. All right. If you have a graph and you want to know if it's one-to-one, remember to determine if something was a function, we did the vertical line test, right? We drag our vertical line across, touches one point at a time, passes the test if it only touches one point at a time. If we want to know if something is one-to-one, we do a horizontal line test. So we take our horizontal line, we're going to drag it up and down on our graph. Again, if it only touches one part of the graph at a time, it's a one-to-one function. So let's run through these really quick. Would this first one on the left pass the vertical line test? Yes, so it's a function. Would it pass the horizontal line test? Take a horizontal line, drag it up and down. Do I touch more than one part of the graph at a time? So it fails the horizontal line test somewhere like here. We say that it is not one-to-one. Okay. What about the parabola in the middle? Is that a function? Does it pass the vertical line test? Yes. Yes. Is it a one-to-one function? Does it pass the horizontal line test? It is not one-to-one. Okay. What about the last one over there? That's our reciprocal parent function. Does that pass the vertical line test? Yes. Does it pass the horizontal line test? Yes. So this is an example of what a one-to-one function would look like. Now, a lot of times when we're doing inverses, we want to be able to calculate inverses of things like quadratics, but we can't do them if we look at the whole graph. So what they're going to do is they're going to take away part of the graph. They might say, use x squared, but only use x values less than 0. Because now if I take away that whole left side, does it pass the horizontal line test? Yes, so you might see like little conditions on some of the problems, and that's because they want us to be allowed to calculate the inverse. We want it to be invertible, and we have to get rid of part of the graph for that to happen. All right, on your big idea worksheet, there are 3 quick little questions. I want to know if these are one-to-one functions, okay? So ask yourself, does each x have one y? Does each y have one x? Or does it pass vertical and horizontal line tests, depending on what you're given? These are going to be just quick little yes or no problems. All right, which one of these is not even a function? Yeah, the middle one is not even a function. Doesn't pass the vertical line test. So it can't be one-to-one. Which one of these is a function but not one-to-one? The first one. Okay, it's a function, but it's not one-to-one because of where? The middle part of the range there. We've got one y value that goes to 2 different x values. And then what do you guys think about that table on the right? That is a one-to-one function. Each x has exactly one y. Each y has exactly one x. Okay? Questions? Cool. All right. There's a quick little problem at the bottom here. You're actually going to see one of these in Math Excel. This is the actual definition of an inverse. So let's say it's one-to-one. We know we can find the inverse. Let's talk about how to get an inverse. In general, when we calculate an inverse, we are switching x's and y's. So it could mean taking a coordinate and flip it, or it could mean taking variables and flipping them, depending on what we're given. In this example, you've got function notation. So the original x is -3, the number inside parentheses. The original y is 12. When we're talking about an inverse, you're going to see this notation. It's going to look like a -1 power, but it shows up between the name of the function and a parentheses. So we know it's not actually taking it to the -1 power. It just means inverse notation. And you're going to notice in the inverse, the x and the y are switched. So if my x was 3 and my y was 12, in an inverse, my x becomes 12. What do you think my y is going to be? -3. That's it. Okay. They just want you to recognize when you see problems like this that the coordinates are flipped when we're looking at an inverse. So x becomes y, y becomes x. It can switch this way if we've got actual numbers or the actual variables themselves when we get to the equations. The next problem on your big idea worksheet is a nice visual of this. If you have a graph and you want to find the graph of the inverse, all you have to do are flip the coordinates, and it's going to perform a reflection for us, but flipping the coordinates will do it, and we don't have to worry about actually using that line of symmetry. So, for example, if I have the point -5, -2, and I flip the coordinates, it becomes what point? -2, -5. Plot that point. -2, -5. That point is on the inverse. If I have the point -1, -1, and I flip the coordinates, what does it become? It is itself. -1, -1. If I have 3, 6, and I flip the coordinates, it becomes 6, 3. And then finally, 8, 8 becomes 8, 8. If you connect those points in the order we plotted them, the same order as the original function, you will see a reflection over the line y equals x, our identity function. Okay, so that's what's happening. So if you have a Math Excel problem and it wants you to identify the inverse, you can think about flipping over that line, reflecting over that line, and recognizing what of the graphs would be the inverse of that. So the red set of dots there is the inverse of the black set of dots. Make sense? Quick and easy little calculations. Okay. All right, so let's say now I have two equations and I want to know, are they inverses of each other? The reason that we did composition in the last section is because you need it to prove that two functions are inverses of each other. If you do composition both ways, if you have two functions G and F, and you plug G into F and you plug F into G, and both times you get exactly X. Everything cancels, but you're left with just the variable X, not an X squared, not an X plus 4, just an X. It is a proof that they are inverses of each other. Okay, so I've got a couple examples here. We'll do this one together. F of X equals 3X plus 1, and G of X equals X minus 1 over 3. I'm going to use composition to show that they are inverses of each other. And then you can always check visually by graphing them and see if you've got that reflection over the line y equals x. So we're going to do composition both ways. F of g of x and g of f of x. It does not matter which one you do first. We're going to plug them into each other. The way I have it written, what am I going to plug into what first here? What's being plugged in? G into f or f into g? This guy is g into f. If I plug g into f, I'm going to take all of function g, plug it into function f, wherever I see that variable at. It looks like 3 parentheses x minus 1 over 3 plus 1. Okay. What I don't want to see on a quiz or a test is you just cross everything out and say equals x. Okay, we don't want to do that. Now, everything will, in this case, cancel out, but you need to show the process of what cancels first and what cancels second. What cancels first here? The 3's cancel first. So if the 3's cancel, I'd be left with x minus 1 plus 1, and then the positive 1 and negative 1 cancel, and I am left with x. So far, so good. If at this point I got anything other than just an x, I would stop and say they are not inverses of each other. I wouldn't need to go on with the proof. Let's do the second one. The second one is f into g. If I plug f into g, that's going to look like a big fraction. 3x plus 1 minus 1 in the numerator, 3 in the denominator. What cancels first? The 1's cancel first, so that would leave me with 3x over 3, and then the 3's cancel, and I'm left with x. Okay, so I got x both times. This is all the work. What's the answer to this question? Are they inverses? Yes. Yes, they are inverses. Okay, and if they weren't inverses, you could say they're not inverses because you don't get x out when you do the composition. All right. Okay, I think the next one is a big idea problem. Go ahead and try it. Determine if these two functions using composition are inverses of each other, and then if you want to check it, you can graph both of them in your calculator and look for that symmetry over that diagonal line y equals x if you want. All right. Let's see. Did you get a no? Okay. Really, there's not a whole lot you can simplify. You should at least have these first two lines on each of your papers, what it looks like after it's plugged in. Now on this one, I foiled it. I don't expect you guys to do that. You can probably recognize at this point things are not going to cancel out and just give you an x. But if you foil it, you're left with this. First terms give me an x. Outside and inside terms are both a -5 square root x. When you add those together, you get -10 square root x. So it simplifies that way, but again, it's not simplifying to x like we want it to. Even this guy alone, we can say it doesn't simplify. You can't take that square root and the squared because of that plus sign underneath there. It has to be a product, things that are multiplied or divided. It could be a quotient under a square root to be able to simplify it. So any plus or minus under there is going to prevent you from simplifying it. all right? So not inverses of each other. Questions there? Okay. The last thing we're going to do in this lesson, and this part might look familiar from if you've done inverses before, is finding the equation of an inverse. These are the 4 steps we're going to use. I wrote them down at the top. We're going to start by replacing our function notation with just a y. Then we're going to switch our x's and y's, which is the actual step of getting an inverse, replacing the variable with one another. Then we're going to solve for y, like we usually do if we have a y in our equation. And at the very end, we're going to put back in our function notation. Okay, so we're going to put a y in for our function notation, flip the x and y, solve for y, and then put back the function notation at the end. So we'll start with a linear one. F of x equals negative 2x plus 3. F of x equals negative 2x plus 3. I'm going to start by, instead of f of x, thinking of it like a y. So y equals negative 2x plus 3. That's the first step. Second step, switch the x and y. Y becomes x becomes y. So x equals negative 2y plus 3. Third step is the actual bulk of the work here. You're going to have to get y by itself. How do you get y alone in this equation? What would be your first step? Subtract 3. X minus 3 equals negative 2y. And then to get y alone, divide by negative 2. And you can just leave it x minus 3 all over negative 2 if you want to there, or you can divide negative 2 into each term. Either one's fine. At the very end, instead of a y, I'm going to put back in my function notation. Now, my original function name was f of x, so I want to make sure I use that. This is not the original function f of x, it is its inverse. So to notate that, we're going to put that little negative 1. It's going to look like an exponent between the name of the function and the parentheses. And that's our answer. If you want to check this answer, the inverse of the inverse will take you back to the original equation. So you could find the inverse again, and it'll take you back where you started. Or you could compose your 2 answers and see that you get x. Or you can graph both of them and look for that line of symmetry over the line y equals x. So a few different ways to do that. Let's try the next one. G of x equals x over x plus 3. First thing I'm going to do is think of that g of x like a y. I'm just going to cross it out and put a y there. Next thing I'm going to do is switch my x's and y's. So x equals y over y plus 3. Now here we have a little bit of trouble because I don't just have a single y, I have multiple y's, and our goal right now is to get the y alone. So I'm going to start by just making this problem easier. The denominator makes it more difficult. So I'm going to get rid of my denominator first. I'm going to multiply both sides by y plus 3. So on the right, I'll just have a y then, if I multiply by y plus 3. And on the left, I'll have x times the quantity y plus 3. Can simplify it even more, just again, making it easier on myself. I'm going to go ahead and distribute that x through. xy plus 3x. Okay, so I got rid of the denominator. I got rid of my parentheses. Now, to get y alone, you want y's on the same side of the equation at least. So I'm going to take that xy and I'm going to move it over to the right. 3x equals y minus xy. How do I turn 2 y's into 1 y? Well, it kind of looks like right now that the y's been distributed through, sort of. We can distribute it, undistribute it, factor it out, okay? I'm going to take a y out of both terms on the right. If I take a y out of both of those terms, what am I left with? 1 minus x. Now I have turned 2 y's into 1 y, which means I can get it alone. How do I get that y alone? One more step. What is it? Well, the y is multiplied by that parentheses, right? And you want to get rid of that parentheses? So what's the opposite of multiplying? Divide by that parentheses. 3x over 1 minus x equals y, which if I put back in my function notation would be g of x with my inverse sign. Okay? All right. Now, continuing with that problem. We just said g inverse was, what was it, 3x over 1 minus x? Right? Okay. When you take x's and y's and switch them, you are also switching domains and ranges. All the x values become the y values, so all the domain values become the range values, and vice versa. So you might see problems that say, find the domain and range and from an equation. Now, we have not done range from an equation intentionally at this point because we haven't known how to do this. If I want to find the domain and range of g, the domain is pretty straightforward. X can't equal -3, right? We've done that before, so it's everything except -3. Negative infinity to -3, -3 to infinity. The range is what causes a problem here because we don't know what's going to come out. It's easier to see what's going to be plugged in. So we use the inverse to help us. What number can x not equal in that inverse? X cannot equal 1. If you set that denominator equal to 0, that is the range of the original equation. Everything except 1. So negative infinity to 1, 1 to infinity. If I want the domain and range of the inverse, they're just flipped. The domain of the inverse is everything except 1. The range is everything except -3. Okay, so if you're asked to find range of a function, it means you're going to find the inverse and find the domain of that. All right, the last two problems that are on your big idea worksheet are going to be our warm-up problems for tomorrow. So I'm going to stop now. You guys can take the last 7 minutes if you want to try those too. We'll go through those at the beginning of the period tomorrow, kind of like we did today. And then tomorrow you guys are going to start in groups working on your test review for your tests next week. We're going to get a little head start on that, okay? So I know originally our calendar said quiz tomorrow. There is no quiz tomorrow, unless you really want to take one. You want to take a quiz tomorrow? No? Okay. So just test review tomorrow. All right, and I'll do the cell phone lotto for you.